Hi Jaydeep. I'm Chandramouli, the TA for this course. So I think I do not know if anybody else will join, so we can get started. So do you have any specific doubts that we can talk about first? Then I can, solve some of the problems, practice problems and problems related to your assignments. Do you have anything in particular?
Yes, sir. I have some problem in quiz week 5 quiz.
Okay, week five quiz. Okay, which one are you talking about?
Sir,
Which
let
week?
me.
Okay, week five. Um, You tell me the question so we can talk about it. Week 5 assignment. Which one?
Next, I open this. Next, I.
Okay, wait. Let me first share my screen. I think I have to share my screen. Now I'll share this Chrome tab. So you can see my screen, right?
Yes, sir.
So which question do you have problem with?
5, 8, and 9.
5, okay, yeah, 5, 8, 8, eighth question and ninth, right?
Yes, sir.
Okay, so all these things I'll be discussing, so we can discuss it over the time. So the thing is, five, 8 and 9. I have question. I mean 8. I have questions prepared for that. Ninth is okay. Ninth is easy as well. So I'll tell at the end. Sure.
Yes.
Okay. Now let me just. Okay. Let me first share my screen a little bit. Right. I think I'll start presenting now. So you can see my screen now.
Yes, sir.
Okay, thanks. So basically, this week mostly it was about few engines and definition of entropy and details related to entropy. So we'll go through some problems related to it. So first, I'll start with a little tricky problem related to engines. So as you know, like calculating efficiency, work done, heat input and heat output, those are quite easy. But then here it's a tricky problem just because of the fact that there are three reservoirs, So 400 Kelvin, 300 Kelvin, 200 Kelvin, but there's just one work being done here by the heat engine. So we'll have to figure out how to do this. So do you have an idea of how to do this? You can take a look at the problem for a minute and then tell me. Let me redraw it. This is T1. T1 is Q1. There is some work being done. Jaideep, any idea?
No, sir.
Okay. So what I'm going to do is, see, these are all reservoirs. So there is a high temperature, probably low temperature, maybe room temperature. So thing is, we are taking some temperature from, they already told that we are taking a temperature, heat for about 5 megajoules from 400 Kelvin reservoir. And some work is being done. So we know that much. But we do not know what the heat that is going into or away from the other two reservoirs. Okay, so we'll call the other two reservoirs as T2, which is 300 Kelvin, and that is Q2, and this is Q3. This is two. This is okay. It's T3. That is 200 Kelvin. So the thing is, this Q2 and Q3 can be positive or negative. Okay, so let's say Q2 is negative, which means that it is the heat is taken away from the system. Okay, let's say I'm directing it like this, but then heat is taken away from the system. So if it Q2 is negative, that means heat is going to go into the heat engine. If Q3 is, let's say, positive, then heat is going to be deposited into this reservoir. All right. So now we'll see from the heat engine's perspective. So now heat engine is the system and all these are reservoirs. All right. So what are the things that we know? So for the heat engine, let's say it's a ideal engine, right? It's it's a reversible engine. Okay, let me just push this down. Yeah, it's a reversible engine. So since it's a reversible engine, what is the equivalence? So there is Q1 amount of work is taken in. So what is the work done here? What I'm assuming here for now is Q2 and Q3 are basically cold reservoirs. Okay. So now, what is the work done? How much input is taken into the system?
We know Q1 equal to 5 megajoules, so
Yeah.
I
So
think
it must be, yeah, tell.
it must be same or higher.
So in general, we can write work done as Q1
1
minus,
plus
see,
Q,
Q2 is going away.
yeah,
Q2,
minus
again
Q2
Q3 is
minus
going away.
Q3.
Okay. So the heat engine, Q2 and Q3 are being put out. So that's Q out. This is Q in. So that remaining work is the work done. Okay. Remaining heat is the work done. All right. So now, how much is the work is 840 kilojoules. Okay. This is 840. And Q1 is 5 megajoules. So I'll keep it as 5000 kilojoules. So all of them are in kilojoules. So then we can get one equation like this. To 5000 minus plus 840, which is basically Q2 plus Q3 is equal to, which is this, 4160. So this is, let's say, equation 1. So we have one equation, all right? But we have two unknown variables, so we need one more equation, right? So we have, what do you know about, Jaideep, what do you know about Cauchy's inequality? Cauchy's inequality.
No, sir, I don't have any idea.
Okay, so it's something that relates entropy and the engines. For a cyclic process, uh, what is the entropy? Okay, before clashes of collective. Okay, we can just do that as well. For a cyclic process, what is the thing? For a cyclic process, what is delta S? Delta S is a state function, right? So cyclic process, it comes back to its initial position. So what is delta S? Same
Delta
position.
is equal to 0 in
Ha,
cyclic
yeah,
process.
correct, correct. You're correct. So let's say there are n number of steps, I number of steps here. So what is delta S then?
0.
Yeah, I mean, I'm asking the formula. Q reversible by T, right? This is the formula, right?
Yes, sir.
So we'll use this formula to solve to get another equation. Okay. So now what do we need? We have Q, which is the heat of the system, and we need temperature. So we have Q2, Q3 and all, and then we have the temperature as well, right? Correct?
Yes, sir.
Huh. So we'll use that over here. All right. So we have Q1. So basically it's going to be Q1 by T1. All right. So this is coming into the system. There are, and then, so generally we put summation. Okay, wait. Put summation. Okay, somebody has joined, so let me admit them. All right. So since so then we have Q2 plus Q3. We have three reservoirs. So all these are going to be equal to this is going to be equal to 0. All right. So this much you understand. So now what is Q1? 5 megajoules, right? So that is this put as, and then temperature T1 is 400. Now you tell me the sign of Q2. So Q2 it's going away from the heat engine, which is the system. So what is the sign of Q2?
Negative.
Yeah, same for Q3, right?
Yes, sir.
Huh. So now we'll assume that, and then we'll put here minus Q2 by what is T2 300. Sorry, again Q3, and then 200. All right, it's going to be 0. So what we'll do is, hmm. So now it's just we just need to simplify. I'll just take it to one side by 3 plus Q3, Q3 by 2 is equal to, what is this, 5000 by 4, right? Okay. I just basically multiplied by 100 and then took this to one side. That's all. So then we'll have, then now I'll just simplify it. 2Q2 plus 3Q3 is equal to 6 into 4 divided by 2. Yeah, it's going to be 7500. All right. So we have our second equation. And we have our first equation over here, which is Q2 plus Q3 is equal to 4163. So 4160. Okay, let me write it here. First equation as q2 by q plus q3 is equal to 4160. All right. So this is something we know. So we can just solve these. We have two variables, two equations, so we can quickly solve it. Let me multiply this by minus 2. So minus 2q2 minus 2q3 is equal to minus 8 2 sorry 8 320. So if we, let's say this is 3, if we add to equation 2 and 3, we would get q, these two will get cancelled. These two will get cancelled if we add, this is just q3, it's going to be equal to minus, what is this? Minus 820. Okay, 820 kilojoules. So this is our q3. Okay, so now we have q3. We can easily get q2 from 1, substitute in equation 1. So q2 minus 820 is equal to 4160. So q2 is equal to, what is this? 820 4980. Okay, so these are our two values. So basically you have q3 which is minus 820. So what does that mean? It is negative. So that means it is opposite of what we assumed, and this is 4980. So that means it is whatever we assumed. So since q2 is minus 820, this direction is going to be reversed. Okay, so basically 820 kilojoules is going to go into the heat engine, and 4980 is q3, and it is positive, so it is going away from the heat engine. So that's what we assumed. All right. So actually in this question, the option second, 820 kilojoules to the heat engine and 4980 from the heat engine is the correct answer. All right. So I'll just write it down here. So it is negative Q3 is equal to A minus 820 kilojoules. Okay. Negative because it is opposite of our assumption. Opposite to our assumption. So which means 820 kilojoules to the heat engine. Okay, to the engine, and Q2 is 4980 kilojoules. So which implies that much from the heat engine. Okay. So we have solved this much. So we can go to the next problem. Huh. So this question, Jenny, do you understand? Do you have any questions? Any questions? Hello. Yeah, there. Do you understand this part, Jiti?
Yes, sir.
Okay. So second question, can you tell the answer for the second question? Just read the question and then tell me the answer for that.
Option A.
Okay, you're correct actually. So, can you tell me why it is so? It is actually straight from the statement. So, can you tell me the statement? Do you remember the statement that two reversible engines have the same efficiency? Chidi?
Yes, sir.
Yeah, so you know this statement, right? Two reversible engines have the same efficiency.
Yes, sir.
Yeah, it's basically based, it's from that statement. Yeah, your answer is correct. All right. So this is okay. So this is some PV diagram that we have over here. Thing is, we need to construct a TS diagram. So do you know how to do that? First, can you tell me what kind of process this is? You can start from 1 to 2, 2 to 3, 3 to 4, 4 to 1. Can you tell me what kind of process this would be?
Adiabatic process.
No, I mean, there are steps there. Some are adiabatic, some are, okay, TS diagram. T is here, S is here. Okay. Um, so this is some kind of engine, so that we are clear, okay? So first, let's consider step 1 to 2. What is it? It is a volume expansion or decrease? You see. So this is the first volume. Okay. How it is. So just tell me whether it is volume expansion or a decrease. One,
First
two.
is expansion.
Yeah, so it is a it is a volume expansion, but we do not know whether it is um probably it is an adiabatic expansion. Okay. Then we have 2 to 3, where there is basically a compression and there is something happening here. Heat is put into the system. Right? It is connected to a heat reservoir. Okay. Do you see that? QH.
Sir, what is QH either? Yeah.
So QH is basically the heat that is coming into the system over here. Okay. From a reservoir. So we have reservoirs, temperature reservoirs. So to maintain the temperature in an isothermal process, you need to put in some amount of heat. Okay.
Okay, sir.
Okay. So first is an adiabatic process. So in adiabatic process, what is the entropy change? That okay. First, tell me what happens to temperature in adiabatic process. It changes or remains the same? Okay, in an adiabatic process, temperature does change, but there is no heat exchange between the surroundings and the system. So, so what is the formula for delta S or entropy change? Let's put it as Ts. Ts is dq reversible by T, right? Since there is no heat exchange, dq is going to be 0, correct? You
Yes,
see
sir.
that? So there's no entropy, there's no change. I mean, there won't be any change in entropy, correct?
Yes,
Yeah. And then there is an expansion over here. So volume is expanding. So what is it? What will there have? What will happen to the temperature? No heat. Volume is expanding. So what happens to the temperature?
temperature will change.
Change, of course. Increase or decrease?
Increase.
Why should it increase in
No heat
expansion?
must
Sorry,
decrease.
sorry, Jyoti, I didn't get you. I mean, there was some block there. Okay. So first, there's no change in entropy. So it's going to be a straight line like this. So now temperature is going to decrease. Okay. So next, heat is going to come into the system. Okay. So then it's going to be positive. Let's draw it like this. Just check. Let me just check all this. Okay. So first, what's going to happen? There's going to be hello. Okay.
Sir.
Just let me just draw the lines so that we can. Okay. So this is going to be expansion, right? So during expansion, what is the relation in adiabatic process? There's another relation there. T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. So basically they are inversely proportional. So volume expands, temperature is going to decrease. So we'll keep like this. It's going to be like this. All right. So next step is isothermal. So temperature is not going to change. Okay. So since temperature is not going to change, but heat is coming into the system, it will be okay. I'll have to change few things here. Sorry. Okay. Let me come like that. Yeah. So one is this, two is this. It goes like this. So then heat is coming into the system, but then volume is decreasing. Okay. So temperature is going to increase. So like this. And then again, it is an adiabatic compression process. So since it's in compression and there's no heat change in this is there's no heat change, this is going to be um, the entropy. The entropy is not going to change, but temperature is going to increase. Okay, do you understand this? So first step 1 to 2, it is an adiabatic expansion. So since it's an expansion and the relationship is inverse, temperature and volume relationship, as volume expands, temperature going to decrease. So it's going to be like 1 to 2. So there's a decrease in temperature, but entropy is the same because there's no heat into the system here. Second step, to maintain the temperature, heat is going to come into the system. So since temperature is constant, it's going to be parallel to x-axis. But entropy is going to increase because heat is coming into the system and this quantity is going to be positive. Okay. Then 3 to 4, it is an again adiabatic compression. So volume is decreasing. That means temperature is going to increase. And since dq is 0, it's going to be entropy change is going to be 0. So again 0, but temperature is increasing. Now the last step is isothermal expansion. So since it's isothermal, temperature is going to be the same and it's expanding. So heat has to come out of the system. So this is coming out, so it is negative. So entropy change is negative. All right. Do you understand this or you need some more explanation?
No, sir, understand.
Okay. So if you understand, then we can go. Okay. Now, so this is a little tricky problem. So what I'll do is I'll go up some space here. Okay. First, see the problem and tell me what you understand from this.
This is the Carnot system, and here common final temperature TF, but
Okay.
we need to calculate the final temperature, and here mentioned initial temperature of the bodies at T1 and T2.
Okay. Okay. Good. So basically, we have two bodies like this. Two bodies like this. Okay. And let's say I'll say this as T1. This is the higher temperature. And then we have a Carnot engine. I'll put it as E. And then they are connected now. Okay. They are connected by the engine. So since they are connected, there's going to be heat transfer from, so there's going to be heat transfer from the T1 to T2. Okay, so that's what they're telling, heat transfer. And that heat transfer will be used by this engine to do some work. So basically here it's going to be some Q1 and it's going to be Q2. And finally, this work will stop, work done will stop because at the end, final, okay, let me just put final is same to, oh, sorry. Okay, let me know. Final, okay. Finally, it will go to, I'll write it below, okay? Final state. Final state, both the temperatures will be the same. So since there's no temperature difference, you cannot do any work after. Okay. So now what they're asking us is what is TF and what is the W? So these are the two things that we need to find out. What is TF and what is W? And they have given us a few things. One is the first both bodies are same. Both bodies have same mass. What are they telling? Have identical bodies, okay? Two bodies are identical, and they have what else do they have again? Yeah, and they're telling U is equal to NCT. And all these is this is same for both the bodies. It's just now dependent on the temperature. Okay. So now, um, so this C, what you see, N and C, and C, NC that you're seeing, which is same for both the bodies, is basically the heat capacity. Okay. So they're going to be the same. Now, how can we write the work done? So work done is equal to what? Q in minus Q out, right? So what have we written? Q in and Q1 and Q2. All right. Q1 minus Q2. So now how will you get Q1? So we have we have the heat capacity. So Q1 is equal to, let's say, let's keep the heat. I'll just write it as, since they are the same material, I'll just write it as C, NC. That's the heat capacity into what? Temperature difference, right? Till it goes to final state. All right. Initial temperature, final temperature, correct? You get this point, right? Okay. Similarly, Q2 is going to be equal to NC heat capacity into the initial temperature, which is sorry, final temperature, sorry, T2 minus T1, sorry, TF T1. Final temperature. Again, here is TF minus T2, correct? So what do we have? How we just have to find the W. We can write it as, yeah, sorry. It has to be the heat inlet, right? So it is to be like this. So this is NC T1 minus TF minus Q2, which is again NC TF minus T2. So what is it going to be? NC T1 plus T2, because minus and minus plus minus, and then minus 2TF, correct? So this is the W that we need. This is the work done, final work done. So if you can see here, the final work done is NC T1 T2 minus 2TF. So this is the correct option for W. But how do we get the temperature now? Is the question. I mean, of course, in the option you can get the temperature, but how do we get the temperature? What can we use to get the temperature? Jari, something we used previously in one of the questions. Again, use the Clausius inequality, okay? They say that for a spontaneous reversible process, delta S is going to be equal to 0, right? So now again we'll use the formula of dq reversible by t is equal to 0. So now what are the steps we have? We have two steps. One is T1 to Tf is one body, higher temperature body is one step, or I'll say not first step, I mean first process, and then we have T2 to Tf, which is the second process. Second process. So for both those process, we need to find the dq and dq by t basically, and then we can sum. Basically, we are just going to sum them. All right. So I'll tell. This is going from T1 to Tf. Then we have dq by t plus going from T2 to Tf, again dq by t is equal to 0. So then we can just simplify this. So we already know what dq is, which is nc. You know what that is, right? Nc, then dt, correct?
Yes,
By
sir.
t, yeah, t1 to tf. Same thing over here as well. T1, sorry, T2. T2 to tf, then nc by t, same, dt, which is equal to 0, correct? So now we'll just do this integral quickly. NC can come out and we can just take it out. So it's going to be NC ln TF TF by T1, right? Correct. Again, similarly, plus NC ln TF by T2, correct, is equal to 0. So now we'll take it to the other side. NC ln TF by T1 is equal to minus NC ln TF by T2. I'll just like this, cancel this. Then, so since this is negative, we can just uh, do the reciprocal of this and that will be positive. Ln T2 by Tf, and then again ln Tf by T1. Take exponential on both sides. So this is so basically going to tell us that Tf by T1 is equal to T2 by Tf. So Tf square is equal to T1 T2. So finally Tf finally Tf value is going to be equal to the root of T1 into T2. So this is the answer that we want. So if we did you follow this, Jadip? Okay.
Yes, sir.
Okay. So then if we go back to the option, so that is exactly what we have here. Root of T1 into T2, correct? And this was the work done that we wanted. So we have all this. Then Now we can solve some Carnot engine problems. Okay, sorry. Can you just read the question and think about the answer? Tell me how we can go about solving this. So what do we have here? So first thing, Carnot engine. So you know the efficiency of Carnot engine, right? What is the formula for that? There are two formulas. Can you tell both? Eta is equal to 1 minus, tell this, Tc by Th, right? And there's another simpler formula, which is, sorry, work done. Work done divided by Q in. Fine. So this formula, these are the formulas that we're going to use in this problem. All right. So first, what do we have here? A Carnot engine converts 1/4 of the heat input into work. So that means W is equal to first condition. Let's say case one. Case one. W is 1/4 of Q in. Correct? So which implies eta is equal to, what is this? W is 1/4 of Qn divided by Qn, which implies eta is equal to 0.25, 1 by 4. I'll just keep it as 1 by 4. So now, but we do not know the cold and hot sources. We do not know what is Tc and Th. But we also know that eta is 1 minus Tc by Th. So which is equal to 1.4. So which implies Tc by Th. I'm just taking this. It's 1 minus 1 by 4, which is 3 by 4. So this is, let's say this is equation 1. We have one equation. We need another equation to solve the problem. So we'll use case 2 for that. Case 2. Now what are they telling? They're telling that when the temperature of the sink is reduced by 100 degrees centigrade, its efficiency is doubled. So basically, now the new eta dash is equal to double, okay, 2 eta. And the cold sink, the sink temperature is decreased by 100 degrees centigrade. Okay. So eta dash, but hot temperature still remains the same. Okay. Dash by Th. And now let's substitute all these things over. It's 2 eta 1 minus Tc minus 100 by Th. We also know that eta is, what is eta here? Eta is 1 by 4. So 2 into 1 by 4 is going to be equal to 1 by 2. 1 minus Tc by Th plus 100 by Th. Okay. So what else do we know? From equation 1, Tc by Th is equal to 3 by 4. Okay. From equation 1, 1 Tc by Th is equal to 3 by 4. So let's substitute all those things over here. So 1 by 2 is equal to 1 minus 3 by 4 plus 100 by Th. Okay, so now let's just simplify this. So this will be 1 by 4, then it's totally going to be 1 by 4. 100 by Th. I correct here, 1 by 4, correct. 1 by 4, yeah. So, which implies TH is going to be equal to 400 Kelvin. All right, we got one part. Now substitute this in equation 1. So Tc by 400 in equation 1, 3 by 4. So which implies Tc is equal to 400. Oh, sorry, 300. 300 Kelvin. Okay. So did you understand this, Jaydeep? Do you understand? Did you understand how I solved the problem?
Yes, sir.
Okay. Do you have any doubts till now? Do you have any doubts?
No, sir.
Hmm. All right. Okay. So next is let's see. Next question is what is the next question? Oh, this is something that you asked, right? Uh, what will be the change in entropy when in the question it's 1 mole of an ideal gas? I've just converted it to n moles. Actually, we can solve it, for without any solve it in general. Actually, still will work. Okay. So, okay. So, do you see this? This is what you wanted, right? This is the fifth question, I guess. Fifth question, correct? Jay? What you there? Oh, Jaydeep. Yeah, Jaydeep, can you hear me?
Yes, sir.
I mean, I asked whether this was the question that you wanted to. This is one of the questions that you wanted, right?
Yes, sir. Yes, sir.
Hmm. Okay, so do you have an idea of how to do this? Let's just solve it in general for now, and then we can substitute all these values later, okay? So first is you have P1, V1, Q1, and the system is converted to P2, V2, T2. But we do not know, so basically we do not know the entropy change for this, correct? And since entropy is a state function, since it, do you want to say something?
No, sir.
Okay, okay. Since entropy is a state function, what we can do is we can construct reversible paths like multiple paths so that we can separate this and then calculate entropy for each of those paths. So now what I'm going to do is I will divide this, okay, into two processes, P1, V1, T1. What I'll do is I'll first use ISO, I'll first use an isobaric path where I keep the temperature, pressure constant. Okay. And then I'll change the temperature to T2. Fine. Let's do this. Isobaric path. Volume will of course change and it will be some other volume. Let's keep it as V dash. Then what I do is I do go in an isothermal path where I have T2 constant now, and I go from P1 to P2 and V dash to V2. Okay, so these are the two paths that I have. So for each of these paths, we can calculate the delta S, correct? So delta S is going to be equal to basically equal dq reversible by t plus dq reversible by t. This is pressure is constant over here. I'll keep like that. Here, temperature is constant, so I'll keep it. Okay. So now, when pressure is constant, what is the dq? Can you tell? Constant pressure. What is dq? Constant pressure.
Volume
dq is what is dq?
T1 by ln T1 by T NCBM ln T2 by
Yeah,
T1.
yeah. I mean that's the final form. So let's CPDT, right? Correct.
Yes.
Hmm. And similarly at constant temperature. So what is dq? Minus W is equal to PdV, correct?
Yes.
And PdV is going to be equal to nRT by V into dV, correct? This is from the ideal gas equation. So now we'll substitute all these at delta S. So basically Cp dt by T what's the temperature range? It's going from T1 to T2, correct?
Yes.
T1 to T2. Okay. So then what's the next part? It's equal to nRT by V dV, and this part is going from V dash to V2. We do not know what V dash is currently, but we'll use it later. Okay, let's just wait for a moment. So we'll just do the Cp ln T2 by T1. Okay, then this is going to be equal to, oh sorry, we missed the T over here, right? Yeah, T was there. So this is nR ln V2 by V dash. Now let's see what V dash is. Okay, let's first. So this is delta S for now. Now we need to find out what V dash is. From ideal gas equation, we know P1 V1 by T1 is going to be equal to P2 V2 by T2. So since it's like that, so P1 V1 by T1 is equal to, so what are the conditions over here for V dash? P1 V dash T2. Okay, so pressure is still the same. P1 V dash by T2. So P1 cancels, which means, sorry, we want, oh yeah, okay. We want V dash, right? So V dash is equal to T2 by T1 into V1. Right? So now delta S. So let's substitute it back. Cp ln T2 by T1 plus nr ln. If we substitute it here, what do we get? So V will be here, so it's going to be V2 by V1. Here it's got T2 by, sorry, T1 by T2. Am I doing it correctly? Yeah. So this is what we would get. Okay. So this is what we would get. We can even further simplify this. Cp minus Cb is equal to nr. So if I separate that, minus nr Cp minus nr. Yeah. Okay, I'll do this. So this ln we can separate, right? Okay. What I'll do is Cp, let this temperature be the same. ln T2 by T1. Then what I'll do is we can separate this term. Do you see that? How do we separate this? nr ln V2 by V1 plus nr ln T1 by T2. Okay.
Yes, sir.
Okay. So now this T2 by T1 and T1 by T2 is there. So we'll make it this negative. What I'll do is I'll take Cp minus nr. Okay. So then we'll have ln as common. ln T2 by T1 as common plus nr ln V2 by V1. So now tell me what this is. What is Cp minus nr? Cp minus Cv, what is Cp minus Cv? nr, right? Do you see this? So basically, so then Cp minus nr is equal to Cv. Okay. So we'll do it Cv ln T2 by T1 plus nr ln V2 by V1. So this is the final expression that we have, and this is what we are after. This is for a general process. Okay. Like without any of the values, we haven't substituted any of the values now. Now we'll see the question and substitute all the values. Okay. Okay. So Jaydeep, what do we see here? Ideal gas. There are n moles. Maybe I'll just change it to 1 mole. What's the point? Okay. 1 mole compressed to 1/4 of its initial volume. So basically, what is V2 now? V2 is 1 by 4 of 1 by 4 into V1.
Yes, sir.
And initial temperature, again, it's heated to 4 times its initial temperature. That means T2 is 4 times T1.
T1.
Yeah, let's substitute all those things. So basically T2 is 4 times T1, and what is this? And then V2 is 1 by 4th of ln. Oh, sorry, 1 by 4th of V1. Okay, sorry. Okay, V1, correct. So we've got that much. Let's substitute all those values here. So delta S is equal to Cv ln 4T1 by T1 plus n is 1, yeah, n is 1, n is equal to 1. So then plus r ln, what is v2? v1 by 4, v1 by 4 v1. Okay, so v1 t1 t1 cancels, v1 v1 cancels, so we have cv. System has become so very slow. Okay, so we have ln cv ln 4 plus r ln 1 by 4. So again we can make this negative, so this will become ln 4. So then delta s is equal to cv minus r, I'll take it as common, and into ln 4. All right, so this is the answer for the question. I think that's the one. Yeah, let me check. Okay, all right, so that part is done. Wait a minute. Did I do some mistake over here? No. Minus W. W is minus PdV. So that is correct. Yeah. Okay. W is minus PdV, right? Jadi, dq is minus W and W is minus PdV. Correct?
Yes, sir.
Yeah, yeah. Okay. All right. So we have another question here related to heat engine. So what do we have here? They have given TC and so can you tell me what are the variables that we already know? Just read the question and tell me that. We have this and it's Q in. Oh, how much is Q in, Jati?
3 kilojoule.
Yeah, 3 kilojoules. And what are they asking us? They are asking us what is the Q out into the coal sink. So how do we solve this problem? What are the formulas for efficiency? I told in the previous question. Can you tell me that?
W by Q we can use.
Okay, we can use that for sure. Correct.
Then
Then,
W
yeah.
equal to QC
Uh,
H minus QC. Then
W is equal to Q in minus Q out that we can use.
yes.
Yeah. Okay. Fine. Now we'll use this and solve the problem. So we do not know W. So let's keep W like this. Q in we know, which is 3 kilojoules. And then 1 minus TC is how much? 300. And this is 400. So basically, we'll take out the zeros. So W by 3 kilojoules is equal to 1 minus 3 by 4, which is 1 by 4. All right. So which implies W is basically 3 by 4 kilojoules. All right. So this is the W, but we don't want W, we want Q out. So what is Q out? W is equal to Q in minus Q out.
You out.
Correct. So we want Q out, which is going to be equal to Q in minus Q, Q in minus W. So what is the Q in value? 3 kilojoules minus 3 by 4 kilojoules. So therefore Q out is equal to, how much is this? 4, 12, 9 by 4. So how much is 9 by 4? Kilojoules, 2250 joules. Kilojoules. Fine. So this is the final answer. Almost 2.25 kilojoules. Okay. Simple. Let's see. Did you understand that part, Jaideep? Do you have any questions?
Yes, sir. Yes, sir.
Okay, good. Now this is another question that you wanted. Tell me how we can solve this. Actually, we have kind of solved this problem already. It's like we use the same principles. Can you tell me? Think and tell me. I have already used the same principle 2 times already. Just tell me the principle, then I'll just use that. Actually, you can solve it yourself. You can keep telling me, and I can just solve it. Just tell first start. Let's start with the principle that we have to solve it with. We have a hot metal, TH, and we have a, I'll just put cold metal like this. Cold metal. So this is TH, this is TC. TH is greater than TC. They are in contact with each other, so heat flow is going to be there like this. So this is the Q. See, this is the Q. Can you tell me how to solve this? Just tell me the principle. We have already used this principle. What is what is the entropy change? Delta S is equal to what? Yeah.
Delta is equal to Q by T.
Huh? Like, how do we say that for the cyclical process? dq reversible by T, correct? Yeah. So now, how many processes do we have here? Final temperature is how much? T. Okay. Both of them are going to go to T eventually at equilibrium. Okay. So how many processes are here? One is hot, one is cold. So what processes do we have? Again, two processes, right? TH to T and TC to T, correct?
Yes, sir.
So since it's the same material, the heat capacity Cp is going to be the same. All right. So first is, again, I'll write it as TH to T is going like this. Then we have dq reversible by t plus for the cold, how is it going to go? It's going to go from Tc to T, correct? Reversible by T. So what is dq reversible? It's like a constant pressure process. So what's the dq? dq constant pressure, what is it? dq is equal to Cp dt. Okay. So let's substitute that. dht Cp dt by T plus Tc to Th, sorry, T again Cp dt. It's the same material, so you don't have to worry. So if we integrate this, what do we get? Cp ln, oh sorry, I forgot, n, no, number of moles, yeah. ncp, yeah, ncp Tc T. What happened? Just a minute. Okay, nothing happened. So T by Th, correct? T by Th plus Ncp ln T by Tc. All right. So how do we find? What do we get? What's the final expression then? We can multiply these two, no? ln T square,
T by th. Yes.
yeah, Tc by Th, Th, Tc, yeah. So this is the final expression. All right. You're clear with this, right?
Yes.
Okay. So basically, it's just the same formula that we have been using continuously. So if you understand that definition of entropy, most of these problems are quite straightforward. So now finally, we have one question before closing. Just tell me this. Sterling engine, did you see the video from Sir's? Did you see this Sir's video? Ideal Sterling engine. Jaideep?
Yes, sir.
Okay. So can you tell me what are the processes in Sterling's engine? What is the first process? 1 to 2. Just tell me whether it is isothermal, adiabatic, or isobaric, isochoric. Just say the step.
Isothermal expansion.
No,
Isot
it is first step is adiabatic. Okay, adiabatic. What is this? Adiabatic compression. Yeah,
this type.
this is a Stirling engine. Okay, ideal Stirling engine. 2 to 3. What is this? Volume is not changing. So what is it?
Isothermal.
No, no. Volume is not changing. Iso what? See, if volume doesn't change, it is called isochoric. Okay.
Isochoric. Yes.
Then isochoric process. Yeah, this is the isochoric process. Then 3 to 4 is again adiabatic expansion. So this is heat, isochoric heat addition. So here you put in heat, so that is QH, that is QH, and heat is taken out here, that is QL. All right. So this is adiabatic expansion. And final process, what is it again? 4 to 1 is, what is it? ISO? What? Isochoric heat release. All right. So these are the processes in ideal Stirling engine. Fine. So now, JDB, you wanted some other one more question, I guess. Let me share my screen first. I'll present something. Ah. So you see the screen, no?
Yes,
So
sir.
you were asking about for an irreversible process, what is the entropy, correct?
Yes, sir.
See, by definition, so basically this is in one of the second principles of second law of thermodynamics. For an irreversible process, entropy will always be above, entropy change will always be above zero. It cannot be equal to zero in an irreversible process. Only for a reversible process, entropy change is zero for the universe. All right. So
Okay, sir.
basically, these are all delta Q reversible by T is entropy, and it is going to be more than zero for an irreversible process. Okay.
Okay, sir.
Uh, yeah. So that's it for today, Jaideep. So do you have any
Can
other
you
question?
see? I want to check my all answer too. Can you see one another time all the
Sorry,
answer
which
in
answer?
quiz question? In quiz question,
Yeah.
you see one more time answer. That can I
Which?
check my which quiz
Okay.
question are you seen again?
Oh, okay. You want to see my answers?
Yes, sir. Yes, sir.
No, no, Jaideep. I've helped you, but then it's like I cannot show it again, okay? Because you'll have to do it yourself. I have tried to cover all the problems. If you use the same principles, you should be able to solve all the problems, okay?
Okay, sir.
Okay, all right. If you have, do
Thank
you
you.
have any other questions?
No, sir.
Okay, 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 then that's it for today. All right, you may leave.